Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything covered in week 1. So we started with index laws. These are the 8 that you need to know, although you would have seen these many times. So rather than go through each one, I'll go through a few example questions where I'll highlight some common mistakes. So let's do this first one here. So the first common mistake I see is when people are expanding brackets with indices, they forget to raise both things to that power. So to do this expression on top, I go 3 to the power of 4, and then x squared to the power of 4. I keep the same base and multiply the powers. That's how you do a power to a power. So on the bottom, another common mistake I see is people think this expression here must be 1, but only x is being raised to the power of 0. So, assuming x isn't 0, this expression would be x cubed times 9 times 1, or just 9 times x cubed. So when you're simplifying an expression with numbers and pronumerals, do them separately. 81 divided by 9, and then x to the power of 8 divide x cubed, keep the same base and subtract the powers, because this line here means divide. All right, let's write this expression in index form using only positive indices. So this is a common mistake I see. People think that this minus 7 needs to go to the bottom. This negative 7 is a negative base. It doesn't have a negative index. It actually has a positive index. So everything with a positive index goes on top, and anything with a negative power, we're going to move to the bottom and write with a positive power. That is the final answer. We don't put negative 7 on the bottom. So another mistake I see is when people try to raise fractions to a negative power. There's a simple way to do it. When you're raising a whole fraction to a negative power, simply flip the fraction and make the power positive. So now we're going to raise the top thing to that power and the bottom to that power, and then we're done. So this last example involves fractional indices, which are going to be very important when we come to calculus. So the common mistake I see with fractional indices is they mix up which number goes on the top and which number goes on the bottom. So if I'm going to write this as a fractional index, so I'm going to keep the same base, the power goes on top, which root it is goes on the bottom. So what would a root a be in index form? Well, this is a to the power of 1 times a to the power of a half. Root a is a to the power of a half. So this is a to the power of 1 plus a half, or a to the power of 3 over 2. And then this works just like all other indices do. The fractions don't change it. We're going to keep the same base and add together the powers. And you can put it on your calculator if you need to get 2.3 or 23 over 10. And we're done. All right, let's now look at scientific notation. So scientific notation is just a convenient way to write really large or really small numbers. So these steps here tell you how to write in scientific notation, but you'll often be told to write to a number of significant figures. So for significant figures, remember numbers in front of the decimal point are significant if they're not 0. The only digits that are not significant are zeros at the start of a number, and usually zeros at the end of a number are also not significant. All right, let's write this number in scientific notation. So we're going to put the decimal point here and follow these steps. So we're going to move the decimal point until this number is between 1 and 10. If I move it here, the number's not between 1 and 10, but if I move it here, the number becomes 9.87654,321. It's now a number between 1 and 10, so that's the number that goes in the first box here. The number that goes in the second box is how many places I moved the decimal point, so I moved it 3, 6, 7, 8. Because this is a number greater than 1, it's a positive 8 that goes there. But this one's said to 3 significant figures. Well, here I actually have 9 significant figures. So to round it to 3 significant figures, I go to the 4th significant figure, 5 or more, raise the score. Because it's more than 5, I'm going to raise this significant figure. So this will be 9.88 times 10 to the power of 8. So what about this number here? Well, it actually has 5 significant figures. All of these zeros are not significant. We're going to write it in scientific notation the same way. So we're going to move the decimal point until the number is between 1 and 10. So I'm going to move it there. That makes the number 8.3121. So it's always times 10 for scientific notation. Now here I move the decimal point 2, 4, 5 spots. So I put a 5 in the power. But because this number is less than 1, the original number is less than 1, the power here is negative. It's actually 10 to the power minus 5. So to 3 significant figures, here the 4th significant figure is 4 or less. So I just leave it like this and then I'm done. All right, let's now look at some exponential graphs. So we're going to look at graphing functions of this form. This is an exponential function because the x, the unknown, is part of the power. So these graphs always have a horizontal asymptote at y equals c, c being the value here. The reason for that is we're only looking when a is positive. If you raise a positive number to a power, you can never get an answer of 0. That's how asymptotes come about. So it turns out the graph is increasing if a is greater than 1, so it'll look like that. And it's decreasing if a is between 0 and 1. So when a is greater than 1, this is exponential growth. The graph increases at an increasing rate. This is exponential decay. The graph decreases at a decreasing rate. So exponential graphs will always have a y-intercept. You can just find that by letting x equal to 0. And sometimes there will be an x-intercept. There's only an x-intercept if this graph is shifted down or c is negative. All right, let's look at graphing something like this. Y equals 2 to the power of x plus 1 minus 3. So c is minus 3, so the asymptote, which is always horizontal, will be down here at y equals minus 3. So I start by putting that in. So what would be the y-intercept? Well, if x equals 0, we get y equals 2 to the power of 1, which is 2, minus 3, that's minus 1. So it will go through there. What would be the x-intercept? This one will have an x-intercept. So that will occur if I have 0 equals 2 to the power of x plus 1 minus 3. So this equation won't give you a rational answer. You can use your graphics calculator to calculate the intercept for you. It's about 0.58. So it's around about here. So if you need more points to determine what the graph will look like, you can use a table of values. You can substitute in any value you like for x and find the y value. So if x is 1, then we'd have y equals 2 to the power of 2 minus 3, which is 1. If x was 2, we'd have 2 to the power of 3 minus 3, which is 5. So it'll be up here and so on. Just plot as many points as you need and it has this shape. So what happens with exponentials is they'll get closer and closer to but never hit the asymptote. So that's what the graph looks like. Be sure to use your graphics calculator to help. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.